Okay, I was just testing. Hello again. Today, this evening, for the next hour, I'm just gonna work on looking over the design brief for the module, the Eurorec module, and deciding, just getting a feel for it. And then I'll start working on the schematic, which I already partly did gradually over the last few months. Just to be honest, this file, these design files that you see here, believe it or not, I was just tinkering with it every day, but now I want to turn it into a real thing. And there's a lot of things I want to change about it. But it's quite good in these videos that I have a lot of groundwork done already, because the initial parts are quite boring and repetitive. So, quick recap. This module I'm designing is going to be, well, I don't need to go into that now because I'm just going to go over the document. It's quite a good idea when you're designing something to have a document. I call it a design brief, kind of like I'm commissioning myself to do something. This is the document here. I'll just make it bigger. I wonder if there's a way. No, that's not the right way. Zoom in a little bit. I'll make it a bit bigger. It'd be quite. I'll be quite quick through this because it can get quite boring and tedious. But these sentences are just to sort of solidify my ideas before I get going. So the whole reason I want to do this the whole reason this was initially started was because of the release of the RP2350 by Rossi Pi, which was last year, I believe. I'm a bit of a fanboy of the RP2040, which was the one that came before, which was an M0 processor, an ARM M0 microcontroller, but I always hoped that they would release one that was good that could do some DSP and could do more audio projects. I did actually design a module for the RP2040, but I never produced it, which is a shame. So I really want to make this work. And so basically there's two sort of keystones in this project. One is I want to demonstrate the RP2350 see what it can do in terms of DSP. It's got a good amount of flash capacity and some interesting interfaces. But here I said with some DSP extra large flash capacity and fast HSTX interface for a screen. Yeah, and I want to release a project that is completely, that can, well, an interesting thing has happened with JLC PCB that you can now basically get quite affordable PCB assembly, and I'd quite like to designs like we can see here. Where's PCB? There's not much on it, to be honest, on the front services, on the front page. But the greatest thing about it is that there's a parts library, so you can see everything that they have in stock. and you can and some stuff is just available with no extra fees for assembly. So it can be quite cheap just to make 5. So the idea is I want to release a project with all the details in it and the libraries to let you get your own modules made at JLC PCB with 0 soldering basically. I've even managed to find jack sockets, and it would just require a little bit of assembly, mechanical assembly mainly, and I'd really like to design a module where, just out of curiosity, if you could design one that doesn't require any soldering at all. Yeah. I mean, are those my 2 main inspirations for the project? I guess the creative inspiration is also... Oops. No. Tabs. Is create a Eurorack module that allows beginners or to advanced users. Can't spell. Add. What? Or advanced users to experiment with ideas through programming. Like, the great thing about these modules is there's quite a few languages supported for them. For beginners, there's CircuitPython, and MicroPython, which are kind of the same thing. CircuitPython's supported by is a fork of MicroPython supported by Adafruit. Has a ton of libraries for it. Has some quirks. Isn't great at interrupts and things like that. MicroPython is a little bit more like standard Python, and you can get a little bit more access to the lower level parts of a thingy of the microcontroller for beginners, and it has a really amazing REPL, which is a bit like a command line interface, or advanced features with SDK. You can get more sophisticated features. Design brief. To design a general purpose Eurorack computing module that can act like a missing module or allow experimental ideas that may not be as cost effective as an individual project. Not only is it about function, but also demonstration of product design, open source processes and testing, some of which I personally will be experiencing for the first time. I quite want to, doing live design is part of it, and I want to find out how to, what's the open source certification, what's it called? Oh, open source hardware. OSWA, that's it. I'd quite like to try this certification process. That'll be a video in its own. Because I do release things open source, but my current strategy for open source is just literally just dump everything out there generously. I'm not hiding anything, and I tend to just take the policy of it's out there, so it's out there, and I don't care what's done with it. I don't care if it's used commercially. So I'd never really use a license because I don't really see a need, because I'm like, if I'm sharing it open, I don't really need to limit it. Someone can profit off it if they like. If I was worried about that, I wouldn't have released it. But maybe, I don't know. I know this isn't about licensing, this is about certification, to make sure that the point in this organisation is to ensure that things are shared usefully. It's like, should I certify my product? I think it just means it needs to have good documentation, which should be quite good. Well, I'll go into that in more detail later. Also, it should not be so elaborate that it becomes too high, that the cost becomes too high. Thinking $100 in small quantities. I'm not sure how that's going to work out. We'll have to find out. It should be constructed from common to source, or come to source, or substitute parts, and it'll be required component specs will be fully documented. Again, I'm talking around it, but I need to talk about generally competing with that, like a missing module to allow experimental ideas to be cost effective. It's a missing module, or allow experimental ideas. I've got to be honest, following on from modules like ornament, crime, or distinct. So interestingly, ornament crime was an open. There's EuroPie as well. So ornament and crime was based on the Teensy 3, and I think they've got a new one coming out based on the Teensy 4. But it's quite an expensive module, the microcontroller, because it's really good. Much more powerful than the RP2350 even. I think it's a, I don't know what it is, a Cortex M4, and it goes really fast. The Teensy 4 goes 4.0 and 4.1 go really fast. The EuroPie, which is based on the RP2040, that's relative because it's based on the Raspberry Pi, but I think it was quite simple, which is quite elegant about it, because it wasn't, the EuroPie is quite a, like, I can show you, well, no, that's not this, or the Disting, which is a commercial product by Expert Sleepers. It's very sophisticated but closed hardware, but I think people write programs for it. But all these three types of modules, they're sort of programmable modules that let you add, like I say, act like a missing module or allow experimental ideas that might not be cost effective as a product. The interesting thing about experimental ideas is that eventually they could become useful. Because sometimes it's quite hard to perceive the use of something. I will go over this. I didn't really know how. I wanted to talk physically about the hardware, but I think we'll just delve into laying out the schematic. But at the core, it's the RP2350B. The B means it's the 80-pin version, and it doesn't have the internal flash. I call it internal, but it's actually, I believe it's a package that's soldered on top for the RP2355? I can't remember what it's called. But as of the last month or so, this chip has become available at GLC PCB. So it has 520 kilobytes RAM. It has, interestingly, up to 16 megabytes of QSPI PS RAM or flash. Now, I didn't realise that the Metro that I was looking at has the QSPI flash and the PGA 2350, which is by Pimaroni, has PS RAM, a PS RAM chip, which is selectable by cutting a chip select pin, or it has a flash. This one. No, I don't know if they have the same pin out. It looks like they do. So I wonder if I designed it into this module, I could just choose which one I want. Because I really don't know how useful. Because basically the idea is we're going to have an SD card in the module. So do we really need a extra flash space? Would it be useful to be able to load up something into a PS RAM, like a big chunk of data from an SD card, and have it load into the microcontroller faster? But I don't know what the bottleneck on QSPI interface is, and I do know, although I know it's not available in CircuitPython, the SD card could be driven by SDIO interface, but I don't know what the speed limit on that is. Because if the SDIO interface is as fast as the PS RAM interface, then I don't really know. I need to find that out. I mean, I can see, this is it. You can get too much into this detail early on. There's two types of processor inside the RP2350. There's the Cortex M33 or the Hazard 3. Hazard 3 is written by in-house. It's a RISC-V processor, which is kind of interesting. But I'm not that super into processors. And I just think the ARM is good enough. You know, it's probably faster. And then the peripherals of the chip are there's basically two of three different serial type interface types. There's two SPI, there's two UART, which is basic serial, and there's two I2Cs. I was thinking the SPI one could be the SD card, SPI 2 is the display, SPI 2 is the display, I2C1 would be a quad DAC, so we can get analog outs, which is a 12-bit DAC. I2C, I'm thinking of leaving it as a STEMMA-QT interface. STEMMA-QT is an Adafruit name for a type of interface. That's standardized, so there's a lot of products you can plug into a STEMMA-QT thing, like extra displays or sensors or other experiments. I thought that might be quite cool. I don't know if it's going to be available on the front. I think it's better available around the back, and then you can just build something next to it if you wanted to play around with it. I don't know. Might keep one serial port for debug. I know that's not the right thing to do, but having serial debug's quite useful. And there's standard Raspberry Pi connectors for that. I'd quite like to keep this interface on it, the Raspberry Pi debug probe. Basically, there's one. What is it? There's one port for. Oh, tell us about the ports. Where's the ports? There's a USB. There's basically a serial bridge. Don't know how useful that is because we've got the USB. I'll also be breaking out the debug port as well. The SWD that uses separate pins anyway. Where is my document gone? The display, I've settled on this. It's a high density display. I want to connect it to the same place where HSTX interface could get to. I'd love to see how fast it could go. I did think about OEM displays from Apple Watches, but I was worried about the MIPI DSI interfaces. They're quite complicated and they're usually undocumented. And there's so many versions, like multiple lanes and 1 lane, 2 lane, 3 lane, 4 lane, you know. It was too much. And I found there's a load of displays around these two chipsets, and they come with these modules where you can get mounting holes in it, so you might be able to just buy a module and whack it in, a lot like people who use the OLEDs, the SSD 13306 modules. That's where I got bored, but I'm thinking, if I go back to this view and open up Inkscape, I should have opened this earlier. Oh, just realised my hair's all standing up an end. Inkscape is loading. No. So I was thinking, I've laid this out roughly. I was thinking 10 HP, and this is the display that I was thinking of, with 2 encoders, micro SD card, a USB input for programming it. There's a reset button there, USB host, 2 audios in, 2 audios out, 4 CVs in, 4 CVs out, 2 gates in, 2 gates out. I sort of had a look at it in person. I quite like 10 HP. The 4 inputs might just use the standard ADC in the microcontroller. I just had to see what that's like. I'll make sure it's referenced properly. 4 analog CV outputs using the I2C, quite slow. Any CV can be repurposed as a gate. Now, I don't know. I might add extra circuitry so that it bypasses the ADC. I had to think about that. 2 gates in and 2 out. 0 to 5 volts. Yeah, they're these 2 encoders with integrated push buttons. You just USB controlled interface for programming and PC module functionality. For example, you could do MIDI to CV. You can even make it act like a sound card. USB host, that's the square one. This should be called program. I don't know what that should be called. And a micro SD card, loading samples, saving samples, recording. Yeah, anyway. That gives a good gist of what I'm trying to do. Now, the next step is I think I want to how does that look? You can read that going. This is the schematic I designed already. It used the PGA 2350. Oh, it's just such a shame I didn't get around to finishing this. So what I need to do is I need to remove that. I could just take you round the schematic. All my inputs are on the left. All the outputs are on the right. Should we make this bigger? Wait, I don't know how to get rid of this. View. Maybe one of these. Yeah, that's it. You see all my inputs on the left and all my outputs on the right. And if you go back to this view actually, the idea is I want it to be a single panel in a single file, which kind of goes against the nature of KiCad. This is KiCad, by the way, which is an open source EDA program for designing circuit boards. You can download it for free if you want. Have a go at it. This will all be on GitHub. In fact, I need to set, that's another part of what I need to do. Maybe I'll do that in this video. I'll set up a GitHub. Basically, the way this works is you do a schematic and then it relates to a PCB layout. But normally, in a design, especially in a Eurorack module type design, you might have multiple PCBs. You'll have one PCB for the connectors and one PCB for the circuitry and another PCB for the panel. So you need 3 different project files with connectors on them, correlating to each PCB. Every single separate PCB you have in the project needs to have its own KiCad project file, schematic and layout. But here I'm trying to avoid that, so I'm doing something a little bit hacky, which is my schematic is just a single file, and the idea behind this project is that I can show a 3D view of it. I'll have it all as a single panel, and it will get assembled as a single panel because that's cheaper. And there should be little tags in there, and it all just gets made as a panel. You crack it apart and assemble it, basically. Of course, we wouldn't have this big PGA thing there. Yeah, so the hack around it is these connections. Also, what I really don't like in designs is using 2.54 headers between boards. I really like using FPCs, where you get a little ribbon that goes between them. It's not ideal because you're sending analog signals really close to each other on a ribbon, but I try and make it as short as possible. It just makes the assembly a bit easier, and saves a ton of board space. So I have this, if we go back to the schematic view, this is the two ribbon connectors on the main circuit board. In fact, I could probably just label them so it's easier to understand. This one is called connector board. What are they called? FPCs. And this one is brain board PCB. I'm doing capitals. And this is a trick to make KiCad. This is a trick to make KiCad full KiCad, and to let me do multiple panels on one board. I was just asking. Misha just asked why I'm not using 1.27mm pins. I don't know, I like using FPCs. I've used them before. These are, what FPCs? Like 0.8mm, so I can get tons of signals through it. Bit dodgy, especially as I'm putting USB through it. But yeah, don't know. It kind of works. Now my brain's got sidetracked. So you see here, this is kind of strange, but I've created nets for the connector board, probably because there's less routing on the connector board. So there's 5, I call it jack board. So I can tell which nets are from which board, and they're called micros. If they're, I guess I should call them. Let's call it jack board. PC, and I like brain, micro board, PCB, FPC. Flat flex. What are they called? FPC flat flex. FFC. Misha asks, it's expensive, but they're quite cheap. Go to, if I show you, if you go to LCSC, they have really affordable, way cheaper than connectors. 2 point, if you go to connectors, connectors, and we go to FFCs. What is it, FFCs? There's too many things in front of me. There they are. FFC, FPC. I chose the most common design, which is 40, I think. It's a 40 pin. It's a 40 pin 0.8. Sorry, just a minute, I'm just looking. It's a 40 pin 0.5mm connector. Oh no, these are the sorry. These are the connectors. The connectors don't cost much at all, they're about 50p. You can buy the cables, and 0.5mm 40 pin. I mean, it is a pain routing, but this is likely going to be a 4-layer board anyway, because the brain part is is quite dense, and I like having ground planes. And I'm going to do quite a short one like this, for example. 5p for one connector. Here, see, one of these. And the idea is that it routes up through here. You can probably see it in 3D view. The idea is it comes out there. These are double-sided connectors. Comes through there, goes through there, and then this is mounted on the back. And looks like it's, yeah, that's the right way around. It comes in like that, so it's a tiny little shortcut. It's going to only need to be about 10 centimeters. But yeah, we'll see how it goes. I don't know. Yeah, not a custom one. I need to sign into chat just a minute. Yeah, I don't do anything custom. Oh god. I thought I almost showed my password for my email account then. Sorry. Hey, Axis Modular. Right. Flat flex connector. What it's called, or flat, oh god, such confusing names. FFC. Let's call it flat flex connector. Don't know why there's a floating 5 volts here. The next, okay, I should just start now. So when I designed this, there wasn't really anything out for the RP2350 apart from the PGA. This PGA 2350 was the only one that came with the 80 pin version on it. So I designed this, and I should have just gone through with it if I hadn't. But now, since Adafruit has released the, where is it? I've actually lost it. Here it is. The Metro. We're going to just try and align it with that design. The great thing about open source is you can look at the schematic. So I'm going to work from this on the schematic. I don't know, maybe I should make a new view. What was I doing though? I haven't yet put power in. Oh no, here it is. Yeah, so this isn't great. I have the power coming in here. Let's call that a 0, 10 pin socket, just so it's clear. Can I add in? No, I can't. It goes into this, I guess, yeah, is a big chunky 5-volt regulator, but it's not fantastic because that's quite a large voltage drop, so it'll have to dissipate a lot of power. And I think it's actually quite good to basically copy this design. I mean, this is probably straight out of the datasheet. It's a 3 amp buck converter, and it can take up to 28 volts input. It's TPS 54302, and they should be available in your parts list. 54302. Oh, I probably didn't memorise that right. TPS 54302. Tons of them, and they cost 20p each. Is the data sheet in English? Nope. Here we go, TPS 54302. So maybe that's the first thing I should do, is put in this. I bet you design is straight out of here in application. So what do they have? Get these close to each other. This is the, yeah, here's an application that shows a 5V output. Yeah, they use a different inductor. I mean, switching buck supplies are quite tricky. Got the V in. I wonder what the voltage divider here is for. Voltage divider. I mean, I wonder what these resistors are for. Application, implication. Boot. Whoa, what's the boot pin? In datasheet you can see, usually it tells you what the pins mean. Supply input for the high side FET get connect to a 100 nanofarad capacitor between boot and switch. Right. Does it tell us what's these resistors on the enable for? Output filter. Oh. Interesting. Recommended output values. R2 and R3. What's R2 and R3? That's probably the voltage divider for the feedback. The 3 voltage. Wait, what? So they've just completely eradicated these strange parts, like weird values like 49.9 ohms. How bizarre. Switching supplies always have very complicated data sheets. All the ripple information. Biaxis. Axis. See, Saturday. Oh yeah, Saturday. There's the synth and pedal show in London. If anyone's around, you have to book it online. It's in Hackney. Yeah. Anyway, I think it might just be good to copy this. I've never seen, I obviously don't design a lot of these switching supplies, I've never seen a boot But it'd be good to see it in context with the internal components. Right. Well, there's too much to go into in the video. I think we'll just copy it. They use quite high values here. That's a tiny value, so this is probably some kind of filtering. Funny. There's probably a series resistor with this capacitor. 100k, 13.3k, 56k and 10k. What I think we'll probably do is just copy this and then come back later and see. I'll probably out of video. I'll probably have a little look at the equations. There's a lot to go through. Bootstrap. Oh, it's called boot as in bootstrap, not boot as in booting. Output voltage set. The only other thing I'm a bit curious about is what is this on the enable pin, the voltage divider on the enable pin. Enable pin, output capacitor, feed forward capacitor. What that is. C6 in parallel with R2, which is, yeah, that's what that is. Just improve phase boost. For this design, C6, the C6 capacitor is not needed when C out has high equivalent series resistance, and C6 is calculated from equation 16. What Adafruit thought it wasn't necessary. Where is enable? I just want to, one last thing. I just want to look at where it says about enable pin. Design equivalent details. Design input capacitor, bootstrap capacitor. Strange, doesn't mention anything. Anyway, I'm just going to copy that. Now, I don't know if the part exists. Go to... You can't see that. Uh-oh. Oh, not that. I had to do it in this. TPS 54302. Hey, it exists. Great. It's a relief when something exists in the library already, in the standard KiCad library. So we need that. We've got 5 volts out. move this out the way. Oh, that's interesting actually. Oh no, that's fine. It's on the same board as the micro. This really needs to be flipped. If you press the keycard, if you press X, swip it around the X-axis. Now ground, it's just a straight ground. I'll switch to this view so you can see straight ground. We literally just tie enable to input. Do we need enable? Yeah. The output has a 10 microfarad capacitor on it, but we're not connecting it straight. We need the, usually best just to find capacitor from somewhere else. I think it's 100M. Oh. Why is the value not shown? Yeah. No. It's the best way to make it look alright. So we need to connect boot to 2. Does that look alright? And we need an inductor. Sorry, read. Oh, you can't see this. I'm opening the library. I want to use an inductor with a ferrite. Now, I don't know why they chose a smaller inductor. 20 milliohm. Is that the saturation? Doesn't seem right. No, it's 5 amp saturation. It's, oh yeah, it's 5 amps saturation, 20 milliohm resistance. With a switching supply, you need to make sure your saturation is high enough, because when the inductor gets saturated, it with current, it becomes less effective, and your switching supply can overheat, become less efficient, and you can get heating. So normally you need your saturation to be way higher. Just need some resistors. Now, this voltage divider reads the 5 volts output, and it's fed back into the feedback pins, and the values are 56k, 10k. And they have a 10 UF They have a small cap, 10 UF cap, small polarized cap. Oh, interesting, they have a sort of big electrolytic capacitor, and then not another electrolytic capacitor, 10 UF. We're using those anyway. 10 UF and oh right, they're just using a couple of multi-layer capacitors, because multi-layers become less effective at DC, and so if you put a few in series, they're less likely to be derate in value. I can go into that, but and on the input we've got another 100M. And a 47 microfarad. I'd probably keep it big. And we've got these already. Oops. Wait, which one's that part of? I've got these already, but maybe these should be bigger. Have a small one. Might need more capacitors here, don't they? I think that would be better. This is better. And then they've got a linear 3.3 volt power supply. I've got that already. That's good. Give you a big view. Sorry. This is boring. Where is my linear power? Where's my 3 volt power supply? Here. Interesting. I have separate linear regulators for the DACs. I don't know. That's a good idea. There's one there as well. That's quite a drop, but I don't think they need a lot of voltage, a lot of current. But there doesn't seem to be any sign of a 3 volt regulator for the 3.3 volts. Probably demonstrating why you don't want to put everything in one big file. I want 5 volts because we've got USB, so we need 5 volts. But where's my 3... Oh. Is that one? I don't think the microcontroller has its own... Is it because it's probably because the PGA 2350 has its own 3 volt regulator? Here's the schematic for it. Yes. Yes. We don't have that anymore. So, these are ultra quiet, supposedly low noise regulators. Are the ones I'm using already. That's not the original manufacturers. XR? I don't know who made the original. They're only half an amp, but they're supposedly height. They're supposedly height PSSR. So high power supply rejection ratio. And the LDOs. As I'm using them already, I can just copy it. Good, I noticed that. So we also need, mainly for the micro, don't think it needs more. Half an amp is quite generous. So out is 3.3 volts and in is not 12 volts, but the 5 volts out of here. It has a funny, oh sorry, you weren't seeing the schematic. I just copy pasted this. So basically, 12 plus and minus 12 volts comes in. Oh, I haven't explained what these are. These are MOSFETs that prevent you from plugging it in the wrong way around. The advantage of MOSFETs is you can they're very low on resistance, so the voltage drop across here is minimal. And you don't need, I remember Aaron Letterman was asking the other day on YouTube if you need a protection diode, but you don't need a protection diode for the gate. Reverse gates also, I can't remember. And it's quite confusing how they work, but basically they prevent you from plugging it in the wrong way around. Then it comes in through these electrolytic capacitors. Like, you have to imagine this is 12 volts coming in conventional current sense, coming in like this. Weirdly, it's like, why is it passing through the body diode like that? But that's because this will be on, because this is a P-type MOSFET. Yes, and so it comes there, it comes out, goes into ground, comes this way. If it's reversed, if this was negative 12 and that was ground, it would be turned off, and the current can't go through the body diode because it's in reverse. Anyway, blah blah blah. Then it goes into our buck converter. Now, I did say I want to work out how to do EMI interference testing on it, and I bet you I'm going to need some kind of filter here, especially if this is switching. We'll come to that later in another video. Then let me just double check this is copied correctly. We have it coming. We probably need another capacitor here. I don't know. Probably need another capacitor here. Let's see. Maybe it will be a filter actually. So comes in enable is connected to input just so it's on. Boot needs the bootstrap needs the 100N going to switch. Then you've got the 3.3 microhenry inductor. Then the voltage divider comes off that and comes into the feedback. It's funny that there's no capacitor here. I just feel like there should be a capacitor going to ground to keep this more stable. I don't know. Then we've got a smoothing capacitor there, and then 2 multi-layer ceramics as well, because these are lower on resistance. Yeah, these got lower ESR, and this is like a big bulk capacitor, and that makes 5 volts. See there, and that 5 volts comes into this regulator. Similar design. It's a linear. It's an LDO one instead, and creates 3.3 volts. And this is for the microcontroller. At the moment, this is PGA 2350. But yeah. Okay, next thing. So we've got our. Go back to the split view. We've got our voltages set up. Now I want to move. Let me check their USB. I think I set up USB on ours. Our USB is here. It's a USB-C receptacle, but with USB 2 interface. So basically, I'm going to be using a connector that looks like a USB-C but behaves like a USB 2. Yeah, so you can see here how it works. It's kind of confusing. You can see how it works. It's reversible, so it has these 2 sides. The CC, I don't know why the CC lines are not connected. Oh yeah, because I'm not taking any current out of it. I need to think about that, because I do know some connectors, some computers won't enable. These might need resistors. The Metro obviously takes power from the USB socket, so it's a bit different. We've got 22 ohm resistors. No, on the CC lines they have the 5.1k resistors. I should probably just put those on, even though I'm not using it. Now what 5.1k resistors means, we want standard 5, because USB-C lets you USB-C lets you have more than 5 volts as a voltage, so there is a negotiation. But that's on a different line. But on the CC lines, you can tell it how much current you want, and I think having a 5.1k resistor tells it that you want 3 amps. We don't want any amps, to be honest, but I want it to work with these Apple connectors. It's usually Apple machines that hate non-conventional. So it's 5.1k to ground. Oh, this will be on the see, it says ground jack because this is on the jack board. It's a bit confusing actually, because if you see the the D minus and D plus are the communication lines to the microcontroller through USB, and I've got this divide here. I should probably use a little line or something. Oh, that's a trace. Wait, a line. Like a dashed line. To show that it's on the other board. Or maybe I need to put dashed boxes, I don't really know. I have it on all of these. Because that means they're going through this connector. Yeah, so I've put those resistors in. I need to research a bit about that. Oh yeah, because the Metro is kind of like an Arduino board. It has a DC barrel connector on it. We're not having that. They have a RGB LED. I haven't thought about LEDs yet. Now let's do the SD card. Now they have another connector that they've recently introduced called the iSpy. If we look at that, if we go to the browser, iSpy. It's the iSpy breakup board. Is it called iSpy? Oh no, it's just called HSTX. It's not the iSpy. Interesting. Yeah, it's funny. I know primarily HSTX is about communicating Is it about MIPI DSO or RGB interfaces? All I know is it's a really fast output serial thing, and but it seems like they've made it MIPI DSO. What does it say? HSDX. Bootloader. Not much chat about it. If we look at the datasheet, see, I don't know a lot about it at the moment. Part of the reason of doing this is just to memory, peripherals. It's a peripheral. HSTX. It's a high-speed serial transmit interface. It's general purpose. It lets you clock up to 8. Lets you output 8 GPIs at a rate independent from the system clock. This could be GPIs 12 through 19. Yeah, so it has to be 12 through 19. But I'm only using the SPI display. Is this even necessary? I just wanted a really fast SPI display. And send from the PO. So let's see, what was it, pins? '12 through 19. Yep. Lane 0, yeah, 12 through 19. But it's got 21 to SDA SEL. Which is controlling daydreaming now. I saw examples of using SPI with it. See, so ST78 using the HSDX SPI clock rate is fully independent. You'll need an LCD module for this, for example. It was tested with a WaveShare ST7899. Wire up the signals as pin XXX defined below, and don't forget to connect ground and VCC and ground 333 to your board. Theory of operation. So zoom in. Each 32-bit HSDX record contains 3 times 8-bit fields. 27 to 20, non-inverted chip select pin. 17 to 10. Inverted DC pin. 7 to 0 data bits. Clock is driven by the HSDX clock generator. We do issue extra clocks whilst chip select is high, but this should be ignored by the display. Packing the control lines in the HSDX pre-flow records makes it easier to drive them in sync with clock without having to reach around and do manual GPO wiggling. These can be any permutation of HM and STX to come in thingy pins. So maybe we don't want to copy, because this looks a lot like MIPI DSI. That's interesting. I'm getting tired now. So it's not iSpy. I thought it was iSpy, which was an Adafruit SPI standard. And the only mention of it is on the shop page, where it just says it's really advanced. So what I want to do is I need to have, I think the best place is to look at the, where's the GitHub? To look at the Raspberry Pi Pico example and think that maybe I'll just copy these pins, 12, 13, 14 and 15. So my display, let's go to the quad view. my display is a, what was it called? An NV3030B. Oh yeah, there's a wave share one. But I just want it from Adafruit. From AliExpress. You can see it just has these pins. So we need to set up the connector. Here, this was the display connector, and I had clock, SDA, serial data, reset, DC, chip select, backlight. Wait, no, what's BLK? No, I don't want reviews. Description. Even here, BLK, yeah, it turns the LED on, it's the backlight, so BLK drives the transistor, which is normally held high. Oh, so it's turning off the backlight. BLK is low, it'll turn off, which is normally high. So you don't need to connect it, so but we'll leave it on. So, I think we'll go with the Pico example of using the HSTX with the SPI, and we'll just fix it. Oh no, but I can't do that yet. I need to put in the RP2350 chip, because currently this is the PGA 2350. I have all these jumpers I was using just in case I need to reconfigure it, but I'm not sure if I need that now. These are all the GPIO. It's quite similar to the real thing, really. We go to the data sheet for the chip. Pin out. The pin out's different. Oh yeah. So I think that's where I should stop now. What I'm going to do in the next video is I need to put in the RP2350 because I can't put in the display. I've sorted out the power, but to put in the RP2350 I need to make, well, there's two things. I'm copying this, but I also should follow. So this is the schematic for the Metro, the Adafruit Metro, which is the RP2350, but I need to follow I think I'll do a whole video just going through this document. Raspberry Pi are quite good. They have these documents that take you through designing a board with their chip. And I do know that to order, where's that page? to order the where is it? To do this, you need to order an RP2350. Oh no, maybe that's changed now. You had to adhere to the example layouts of the design guide. So on the next video, which hopefully is tomorrow night, or during the day tomorrow perhaps, is... where's it gone now? Oh yeah, this. I will follow this document, which will introduce differences. We'll go through power, and then we have to go through the memory. The interesting thing about the RP2350 is the memory is separate, which is quite unusual. Most microcontrollers have internal flash, but the Raspberry Pi chips all have external. It's a cost thing, I think. Do the crystal oscillator, and then IOs, USBs, GPIOs, the debug connector, buttons, all that business. Yeah, that'll be another video. Anyway, if anyone's still there and they're bored, congratulations, you made it to the end. Thank you very much. Bye.